Hi, my name is Jackson Petty, and today I'm presenting on behalf of my co-authors Michael Wilson and Bob Frank our new tackle paper, How Abstract is Linguistic Generalization in Large Language Models? Evidence from Argument Structure. So you may have noticed recently that large language models have gotten quite good at a wide array of tasks. We want to understand how good these models are from the perspective of something linguists might be interested in, namely, what exactly do these language models know about the language that they've learned? In order to answer this, we want to measure these models against the kind of knowledge that we know humans have about their own language. So I'll spend a little bit of time first exploring what it means for humans to make use of their own language. And then we'll discuss how we can test for similar knowledge in large language models by teaching them new words and studying what happens when they use these words in novel contexts. And to give you a sense of where we're going to end up with these experiments, the conclusion that we ultimately come to in this work is that large language models' knowledge of language is meaningfully different from that of humans, in a way which leads them to fail at making the kinds of functional generalizations which people are very adept at. So, let's start with what exactly does it mean to know a language? And since we're all living in the era of ChatGPT, I thought it would be fun to start with some basic prompting. Now, if I show you a sentence like, I sprayed the blank on the blank, what would you want to fill in to these spaces? Well, if you're an English speaker, you'd probably agree that we could put in paint for the first blank and wall for the second. These words seem to fit well. This, of course, is more than just knowledge of what would be grammatically correct here, since both of these words are nouns, but flipping the order that we show them doesn't seem to be quite likely. That is, we're much more likely to prefer I sprayed the paint on the wall than I sprayed the wall on the paint. Being able to do this is what we're going to call type 0 knowledge. That is, can you fill in the blanks in a sensible way? And of course, people are quite good at that. But people know much more than this. We also have the ability to make structural grammatical generalizations. That is, conditioned on knowledge that I sprayed the paint on the wall is a good sentence, you know that lots of other sentences are plausible as well, such as I sprayed the wall with the paint, flipping the argument order by changing the construction, or the paint was sprayed onto the wall, making the construction passive, or something like it was the paint that the workers sprayed the wall with, it-clepting. Here we make functional knowledge of the thematic roles that are associated with each of these arguments. Since paint is the theme of this construction, we know that it can go anywhere that themes can go. And since wall is the goal of the construction, it can go anywhere that goals can go. We don't have to learn these positions independently for each of these constructions. This kind of functional abstraction is what we're calling type 1 knowledge. But human linguistic knowledge is even broader than this, because it's not tied to any specific thematic roles or even lexical items. For instance, if I give you a sentence like, I verbed the X with the Y, then you could infer that there are a lot of other related sentences which are good as well, such as, the X was verbed by me with the Y, and it was the X that I verbed with the Y. Now, not only do you not need the semantic information of what verbed X and Y even mean, we also know that we don't have to learn these particular constructions independently. Knowing that I verbed the X with the Y is a good sentence is enough to let you infer that all of these other sentences are good as well. This higher level abstraction, which abstracts over the specific structures involved, is what we call type 2 knowledge. Now, the main question for our work is trying to understand where large language model generalization fits on this chart. That is, how abstract is their linguistic generalization? Now, being able to fill in the blanks well is basically what masked language modeling is. And so, unsurprisingly, language models are quite good at this kind of distributional generalization. In our work, then, we're focusing on these two higher order kinds of abstraction. First, can language models make use of thematic roles to generalize well? And second, can they exhibit structural generalization that goes beyond the specifics of particular thematical roles or particular lexical items? We present two experiments to test this. First, we explore whether models have type 1 knowledge by taking some off-the-shelf BERT-style models and teaching them some new words. Thax, which is a theme-like word, and gorks, which is a goal-like word. Now we're going to freeze everything except for the embeddings of Thax and gorks. And then we're going to train the models on some simple active voice sentences which will teach the models that Thax is theme-like and Gorks is goal-like. For instance, I sprayed the Thax onto the door, I sprayed the paint onto the Gorks, I sprayed the door with the Thax, and I sprayed the Gorks with the paint. We then construct 78 different linguistically sensible generalizations which use these novel words in new constructions, and test to see whether or not models can generalize their understanding of the theme-likeness of Thax and the goal-likeness of Gorks to these new constructions, such as, it was the Thax that the Gorks was sprayed with, or I wonder which Gorks the man seemed to have sprayed onto the Thax, or 76 more. So, how do BERTs do at this task? Well, it turns out that they perform quite well. Across the board, models are very robust at preferring the correct novel noun in the appropriate position given its thematic role. That is, given a theme-like position, models know to choose Thax instead of Gorks, and given a goal-like position, they know to do the opposite. How are they able to do this? Well, they do the one thing that they can do, which is to learn contextually useful embeddings for these novel words. For instance, for spray, we find that Thax tends to move close to other mass-like nouns, while Gorks moves closer to other count nouns, since the themes of spray tend to involve mass nouns, while the goals of spray tend to involve count nouns. So, Experiment 1 shows that BERT models do exhibit type 1 knowledge of language pretty robustly, and they're able to do so by bootstrapping their knowledge of existing language. They learn to put novel embeddings close to other plausible completions. This embedding space turns out to be functionally useful for the kinds of linguistic generalizations that we're asking these models to make. But what about type 2 knowledge? Well, to test for type 2 knowledge, we're going to follow a similar pattern to Experiment 1, but instead of teaching BERT novel nouns, we're going to teach them novel verbs. Here, we're going to construct a new verb, blork, which has some novel selectional properties. In particular, the subject of blork is always going to be red, while its object is always going to be yellow. For example, a valid sentence involving blork might be something like, the fire truck blorked the sun. We'll then fine-tune our models on a set of active sentences with a variety of valid subjects and objects, and then evaluate how well the model can generalize by testing on a broad range of examples which use blork in different grammatical constructions, and see if the models can put the correct kind of noun, red or yellow, in the correct spot. That is, we're going to evaluate on sentences like, the object was blorked by the subject, or it was the object that the subject blorked, or the subject always blorked the object. So, what do we see? Well, unlike in Experiment 1, we find that models are unable to robustly generalize the argument positions of novel verbs beyond the original training context. In particular, we note that the success of models is very dependent on whether or not the linear ordering of the argument positions matches what was found in training. For instance, when we look at validation sentences which are subject, verb, object, such as simple active sentences like the subject blorked the object, models seem to do pretty okay. This corresponds to the second column in our table here. When we have object, subject, verb sentences, such as which object has the subject blorked, or subject, object, verb sentences, such as which subject was the object blorked by, we see that models seem to perform roughly at chance. That is, they're not categorically failing this task, but they're not categorically succeeding either. And when we have object, verb, subject sentences, such as the object was blorked by the subject, involving a passive construction, where the linear ordering is exactly the opposite of what was seen during training, models fail robustly, almost always preferring the wrong noun in each position. So, we find that models don't seem to exhibit type 2 knowledge of argument structure, which abstracts across lexical items and thematic roles. One possible reason for this is that the selectional preferences of this unique verb that we've constructed mean that there isn't any way for the model to bootstrap its way to success by placing our novel verb near other verbs that pattern the same way. Because by design, our novel verb has unique selectional preferences, which means that no existing embedding matches this kind of distribution. Since they can't rely on this embedding space geometry trick to solve the task, they resort to things like linear heuristics, rather than a more linguistically plausible generalization. So in conclusion, our work here shows that large language models seem robustly capable of exhibiting type 1 knowledge, generalizing their understanding of novel nouns to a wide array of constructions on the basis of the learned thematic roles. They do so by exploiting properties of embedding space geometry, placing novel tokens near other tokens with similar thematic roles. This, in turn, allows the models to functionally generalize distributional knowledge to new constructions. But when we remove this ability and instead teach models novel verbs which have distributional properties unlike anything that they've seen before, models can't exploit this subspace trick to bootstrap their way to success. Thus, when we ask models to generalize their knowledge of novel verbs to different constructions, they fall back to simple but linguistically implausible heuristics, meaning that they don't exhibit the kind of type 2 knowledge of language that humans possess. Thank you all so much for coming to our talk, and I'd be very happy to answer any questions that you have.